Hello everyone. In this video I am going to explain the structural realization of the discrete time LTI systems. Now while talking about the structural realization, that is structural implementation or design of discrete time LTI system, first of all we should see what are the different possibilities are there while implementing a digital filter or digital LTI system. Okay, so basically while we go to implement the discrete time LTI systems, or in general the filter, we mostly focused on the impulse response of the system, that is your h of n, and its z transform, that is h of z, which we call as the transfer function of the systems. Okay, so the impulse response is the main key point of designing or implementing the LTI systems, or in general the filter, and equivalently the h of z. Okay, so depending on the h of n, that is the impulse response of the systems, the LTI systems can be further classified as FIR, that is finite impulse response, and IIR, infinite impulse response. So in this video particularly I'll explain the realization, basic realization for the FIR and the IIR systems. So in my next video I'll explain in detail about the FIR structural realization and consecutively the IIR structural realization. Here I am going to share with you basically what is FIR, what is IIR, and depending on the realization, again that the structure or the realization can be recursive and non-recursive. So basically in this video I am going to share with you the FIR, IIR, and recursive and non-recursive. Okay, so let's start. So FIR and IIR systems. Now for any discrete time LTI system, any discrete time LTI system for any arbitrary input, say x of n, output say y of n, the response n, the system is characterized by the impulse response y of n. So for these known LTI systems, that is known impulse response h of n, the y of n can be represented as the convolution sum of the input and the impulse response, that is sum over k minus infinity to infinity x of k into h of n minus k. Okay, or equivalently the same y of n can also be like summation over k minus infinity to infinity h of k, because convolution is commutative, so h of k into x of n minus k. Okay, so now look at these, either these or these, into equations where in general the sum goes from minus infinity to plus infinity. So practically it is not feasible to realize, right, since it is minus infinity to infinity. Another important thing is the LTI systems in physically realizable system means in real time it has to be causal. Okay, so what is the causality condition of LTI system? The causality condition of LTI system is your h of n must be 0 for all n less than 0. Okay, so that means practically this equation will be your like this. Since h of k or h of n is 0, so it will be k 0 to infinity h of k into x of n minus k. Okay, so this should be the practically that means the causal condition for the LTI systems, that is if h of n is 0 for all n less than 0. Okay, now then also it is 0 through infinity. Now depending on this h of k or say h of n, if this h of n is a finite quantity, okay, finite quantity or finite length sequence, finite length, okay, so then this y can be written like y of n some k is equal to say 0 to some say n, okay, h of k into x of n minus k. So this where n is that finite length, okay, capital N is this finite length. So y of n, which is your k 0 through n, h of k x of n minus k. So in this case, since my h of n is finite, for which the output or the response y of n, which is equal to 0 to n minus 0 to n and h of k x of n minus k. So in that case, this system is called FIR system. FIR systems, finite impulse response systems, okay, finite impulse response system, since the impulse response h of n is finite. Now if we do the Z transform both side of this equation, what we will get? Y of z is equal to summation over k 0 to n or say n minus 1, then so since it is 0, if the length is say n, then it will be 0 to n minus 1, okay, so it will be h of z into z to the power minus k x of z. No? So here there is a mistake. This will be your h of k only, because this summation is over k. This summation is over k. So therefore this will be your like y of z summation over k 0 to n minus 1 here h of k into z to the power minus k x of z. So therefore y of z divided by your x of z is equal to summation over k 0 to n minus 1 h of k into z to the power minus k, and this term which is your h of z, okay, which is your h of z. So your h of z is equal to summation over k 0 to n minus 1 h of k z to the power minus k, okay. So if we look at this h of z for an FIR system, finite impulse response systems, is a finite degree polynomial. So it will be h of 0 z to the power 0, h of 1 z to the power minus 1, so on and so forth. So it is up till n. So it is your finite degree polynomial, okay. So that can be implemented. Now again go back to the equation, same causal equation, difference equation. Y of n is equal to summation over k 0 to infinity, so h of k into x of n minus k, okay. So in this case, now if the impulse response, this impulse response is infinite, okay, that means 0 to infinity, the sequence is of course it is 0, h of n is 0 for n less than 0, but suppose n positive, it is non-zero, that means up till infinity, 0 to infinity, it is non-zero. Now in that case, since it is infinite, so what we can say here is that the system output, this output y of n, is the weighted linear combination of the input signals, samples x of n, that is x of n minus 1, x of n minus 2, that means all the past inputs. Okay, so linear weighted sum of the output is the linear weighted sum of the all the past input samples. So where h of n, that means h of 0, h of 1, h of 2, like that, these are the coefficient, I mean the impulse response coefficients are constant, and the output is the linearly weighted sum of all the past input. That means you need to store all the past inputs, so you need infinite memory, so that is also not possible practically. So therefore what we do is we can represent this something like this: y of n is equal to minus this equation also we have already talked about, minus summation over k is equal to 1 to say n y of n minus k plus summation over k 0 to m x of n ak. So here it will be ak, and here it will be some constant bk. So this ak bk constant, representing the h of k, so x of n minus k. Okay, then it is realizable. Okay, physically, practically realizable. Now the system in which the impulse response is infinite is called IIR system, infinite impulse response system. Okay, so based on the impulse response, the systems can be divided in two categories: FIR and IIR, finite impulse response and the infinite impulse response. So likewise in the FIR case, that h of z, as you have seen, is an finite degree polynomial. Okay, finite degree polynomial. But here if you see that h of n is infinite originally, so since it is originally infinite, so it is an infinite degree polynomial. But since it is infinite degree polynomial, we cannot simply realize it, so therefore we make it finite by doing so. Okay, so in that case, if we now take your z transform both sides, then what you will get? For this you will get y of z is equal to minus summation over k is equal to 1 to n ak into z inverse k y of z, and plus k is equal to 0 to m. So when you take the z transform of this equation, it will be y of z minus k is equal to 1 to n ak z to the power minus k y of z. So similarly, if we take the z transform for this, it will be this. Okay, then just simplification. So this, that side, y of z, and this part. So y of z by x of z, which is nothing but your h of z, is summation over k is equal to 0 to m b k z to the power minus k divided by 1 plus k is equal to 1 through n a k z to the power minus k. Now see, why actually we did this? Because in FIR it is okay, since the your impulse response is finite. Okay, impulse response is finite here, so it can be implemented directly. So it in your the transform, it is a finite degree polynomial. The transfer function is a finite degree polynomial. But in case of the IIR, since the equation is 0 to infinity h of k x of n minus k, and where the h of k, that is the impulse response of the system, is an infinite length sequence. So since it is an infinite length sequence, so practically we need to have an infinite numbers of memory to store all the past values, infinite numbers of past values. So instead of going through the direct formulation of the convolution, that means the response due to any arbitrary input with the response of the LTI system due to any arbitrary input x of n through the convolution, will rather we go through the difference equation that characterize the systems. So if for any nth order systems, the same infinite sum can be of like this. Now if we look at this the transform, so it is a numerator polynomial, this is a polynomial, this is also a polynomial. So this numerator polynomial divided by denominator polynomial. Okay, so when you take the inverse the transform, so this is h sub z, so if you take the inverse the transform of this, you will get h of n. So an mth order polynomial and this is nth order polynomial, if you are dividing, you will get an infinite polynomial here. Okay, so that means this h of n, if you do the inverse transform, this h of n will be infinite. But then you can realize it, because this is a finite polynomial, this is also a finite polynomial. But a finite polynomial divided by the finite polynomial may be infinite polynomial. Okay, that means h of n is infinite. But practically to realize it, we go through this process, and in z domain or in the transfer function, it is in this. Okay, now if we look at the equation of your h sub z of the FIR, okay, or if we say this yes, from this equation, this FIR equation, so this y of n is nothing but, say, h of 0 into x of n minus 1 plus h of 1 into x of n minus 1 plus h of 2 into x of n minus 2, and so on and so forth up till a finite n. Okay, so that means in this equation the output at an instant of time n, output depends on the present input, that is x of n, and all the past input. Okay, all the past input. So it does not have any feedback. The same you can see from the h sub z also, because this h sub z is just a finite degree polynomial. So what is h sub z? H sub z is your y of z divided by x of z. So it will be of this type. Already it is there, y of z by x of z. So it will be what? It will be some constant coefficient, say h of 0 into z to the power 0, that is minus 1, plus h of 1 into z to the power minus 1, and so on and so forth. Now if we derive the equation from this, so y of n will be, that is inverse transform, y of n will be your h of 0 into x of n, then plus h of 1 into x of n minus 1, plus h of 2 into x of n minus 2, and so on and so forth, it will go on. So that means at an instant of time n, y of n, that is the output y, is depends on the present input and all the past input for some constant coefficient h. This constant coefficient h is nothing but the filter or the system coefficient. Okay, so it does not have any feedback. It does not have any feedback. That means this output y at an instant of time n does not depends on any past output. That is, it does not have any feedback. So in those kind of systems are called non-recursive. Okay, non-recursive system. Okay, that means non-recursive system means the system in which the output at an instant of time depends on the present input and maybe all the past inputs, but not any past output. But if you look at this, in this equation, this h sub z is this, so h sub z yz divided by x sub z, from which if you go back you will get this equation. So what is this? This is at any state of time n, it depends on the present input, some past inputs and past outputs. So this is your past outputs, that means it has some feedback. Okay, so that means any system that depends on the present input, past input, also it depends on the past outputs, that means it has a feedback, are called recursive system. So this IIR is recursive. Okay, recursive system. So in general, by default, the FIR is non-recursive and IIR is recursive. Now let us look at in a general form what is recursive and non-recursive. And remember, this FIR is by default non-recursive, IIR is by default recursive. Okay, but the recursive can also be realized non-recursively and non-recursive can also be realized recursively. Okay, let's see. So let us start with the recursive. Okay, recursive system. So what is recursive systems? The systems whose output y of n is at any instant of time n depends on the present input and past input, and importantly, most importantly, all the past values of the outputs, that is y of n minus 1, y of n minus 2, y of n minus 3, like that. So this system is then called recursive systems. Suppose that we wish to compute the cumulative average. Just for example, cumulative average. You can think of your bank account where every month you are depositing some amount. Forget about the interest. Suppose there is no interest calculation. Then at any month, at any time, if you would like to see the amount, total amount deposited, which is we call the accumulator, and if we divide by the total duration, then it is cumulative average. Okay, so suppose we used to compute the cumulative average of a signal, say x of n. In the interval, suppose k 0 to n. Okay, 0 to n. So that can be defined like y of n, which will be equal to summation over k 0 to n x of k. Okay, k 0 to n x of k, and if we divide it by n plus 1, because it is 0 to n, so n plus 1, then it is called the cumulative average system, where n is equal to 0, 1, 2, maybe any n. Okay, now as this equation, the computation of the yn requires the storage of all the input samples xk for 0 to n. Okay, since n is, if the n is increasing, suppose for example n is say 5. Okay, n is say 5, then what we require, actually it is we can write it as x of n minus k also. So suppose n is equal to 5, so at the 5th month, suppose January, February, March, so what we require, x of 0, x of 1, x of 2, x of 3, x of 4, x of 5. So just imagine your bank account. Suppose from January suppose n is equal to 0, February 1, 2, like that, and at the December, suppose n is equal to 12 is the December. So you are n is equal to 11 is your December. So suppose you would like to calculate the total amount deposited at the month of 11, December. So what you required? You required the amount you deposited at January, amount you deposited at February, like that. That is x of 0, x of 1, x of 2, x of 3, then add it up. So x of 0 plus x of 1 plus x of 2 plus x of 3, like that up till x of 11. So then it is the total sum. And if we divide it by 12, then it will give you the cumulative average. Now, if suppose n increasing, n is increasing means what? Your memory requirement is increasing because you need to store it somewhere. So memory requirement is increasing. Okay, and as we know, memory is directly related to the money cost. So if n increasing, then the memory requirement grow linearly with time. So better what we can do is we can write it like, okay, if we realize before that, if we realize this system directly, then it is called non-recursive system, because in this system there is no feedback. Okay, there is no feedback, so it is a non-recursive system. It requires only the present input as well as all the past inputs. Okay, so here there is no past output, so it is, that means there is no feedback, so it is a non-recursive system. Now let us simplify a little this equation. So n plus 1 into y of n is equal to summation over k 0 to n x of k. So now if we write it like summation over k 0 to n minus 1 x of k, then what will be the last term? One term left behind, that is your x of n. Okay, so then this particular term, how you can write? When it was n plus 1 into y of n, it is 0 to n. So when it is 0 to n minus 1 x of k, then it will be n y of n minus 1, right? Again let me tell you, when n plus 1 into n, it is 0 to n x of k. So now it is 0 to n minus 1 x of k, so it will be n into y of n minus 1 plus x of n. Okay, so here it will be n plus 1 y of n. So from which easily you can get y of n is equal to n divided by n plus 1 y of n minus 1 plus 1 by n plus 1 x of n. Now look at this equation. So in this equation, at any instant of time n, if you are calculating the output, it is for that instant, it is a constant, and it is just the past output. Okay, plus 1 by n plus 1, this is again a constant, x of n, the present input. Now you see, when this system you realize you need only two memories, only one memory, that means to store just the past value. Okay, past value of the output, and there is no past inputs, only the present inputs. So this is called recursive. Okay, this is called recursive system. Okay, this is what is called recursive systems. Now the cumulative average can be determined, but this cumulative average can be determined by multiplying the previous output y of n minus 1 with n by n plus 1, then multiplying the present input by 1 by n plus 1, and then add it up together. Okay, add it up together. So thus the computation of yn by means of this equation requires two multiplications and one addition and one memory location to store y of n minus 1. So that can be illustrated in your block diagrammatic or system representation as like this. So here, as you see, this is the x of n. This is the symbol for multiplication. So this weight, actually weighting. This is the adder. Now in adder there can be only two input, remember, and this is the inverse block representing the delay or the memory. Okay, so if suppose it is y of n minus 2, then you need to type 2, you need to have 2 z inverse block. Okay, so there are few symbols we will be using. I'll tell you these symbols. So this is one symbol. Suppose this is a and you are applying x of n, it will be a into x of n. So it is the with or scalar multiplication. Then this is your summation, also the plus symbol. Suppose this is your x of n and this is suppose your y of n, and it will be x of n plus y of n. Okay. If it is more than 2, then you need to have again here, not again 3 input here, only 2 input, because addition can, this operation addition is performed once at a time. That means 2 data added at a time. Okay, and for the subtraction you need to just put a minus here. Okay, if I put it minus, so it will be plus or minus. Now this z inverse, this is the symbol. Suppose this is x of n, here it will be x of n minus 1. Okay, and if it is advance, this is delay, and advance it is simply z, but practically there is no advance, that is future output or input is not possible. And for multiplier, it is the multiplier x of n into y of n, like that. So these are the basic symbols we will be using in our structural realization while drawing the structure. So finally, the recursive system are the system that whose outputs is expressed in general as say y of n. Output of any recursive system in general represented as a function, that means the operation of all the past outputs, say like y of n minus 1, y of n minus 2, so and so forth, y of n minus n. Okay, that many outputs, past outputs, then the present input, and all the past, maybe all the past inputs, x of n minus 1, x of n minus 2, like that, x of n minus say n. Okay, so this is the definition of the recursive system. That means the recursive system at an instant of time and depends on all the past outputs, present input, and maybe past inputs as well. Okay, so this this denotes some function of its arguments. These are the arguments. Okay, now a system whose output y of n at an instant n depends only the present input, present and past inputs, not the output, is called the non-recursive system. So this is your recursive system. Similarly, for the non-recursive system, it will be your y of n is a function of all the past inputs, present and past input, x of n, say x of n minus 1, x of n minus 2, and so forth, say x of n minus n. Okay, it does not depend on the present past output. So this is non-recursive. This is recursive, this is non-recursive. Okay, let us see. So till now what we have seen, that the FIR and IIR system. So FIR means finite impulse response. If you look at the output equation of the FIR output equations, so y of n, this k0 to n minus 1, this is a non-recursive equation. Okay, that means FIR is by default non-recursive. But with an example we have seen that the non-recursive system, that cumulative average, that non-recursive system can also be designed recursively. So likewise, although by FIR is default non-recursive, but we can realize it recursively as well. Okay, so because this h sub z here, as you see, this h sub z is a finite degree polynomial. Say here it will be h sub 0 into z to the power minus 1 plus h of 1 into z to the power minus 1. So in terms of difference equation, we may put it as say bk. So h of k instead bk, so b0 h of. Similarly, if we look at the IIR, in the IIR system, it is this h of n, which is an infinite polynomial, can be represented like this, and where if you look at this yn, from this to yn or from this yn to this hz. Okay, so if you look at this yn, then you will see this all the past input and the present input plus all the past output, which is recursive. Okay, so by default IIR is recursive and FIR is non-recursive. Okay, if you look at the polynomial here, so it will be a numerator polynomial with the constant coefficient b and with the denominator polynomial with the constant coefficient a. Suppose this a0 is also present, just for sake of simplicity a0 is also present, although here I have given from a1. Suppose a0 is also present. If this a0 is also present, then a0 will go with the yz, so it will be a0 into yn, then whole equation you have to divide by a0 if a0 is not equal to 1. Okay, that is another issue, but it is numerator polynomial by denominator polynomial, which is the recursive. So whenever there is in a transfer function there is a numerator polynomial divided by a denominator polynomial, that means the system which has both zeros and poles are called recursive systems. Okay, now when there is only zeros, there is no poles in the transfer function, then it is called non-recursive system. That means all zero system is a non-recursive system, and pure recursive is all pole system or zeros and poles. Okay, poles and zeros already you know. So in this transfer functions, in this numerator polynomial, the roots of the numerator polynomial for which this transfer function is 0 are called the zeros, and the roots of the denominator polynomial for which the h sub z is infinite are called the poles of the system. So finally, in general, an FIR system can be always be realized through a difference equation in which the past value of the output are not present, that is, in a non-recursive fashion. An IIR system can be realized directly from the difference equation in the form of a recursive relationship, because the past value of the outputs are required in the realization. So for this reason, the terms FIR and non-recursive are sometimes used synonymously, and similarly IIR and the recursive also. However, in practice, an FIR system may also be realized in recursive fashion, and IIR system may also be implemented by non-recursive systems. One example already we have seen. Let us see another example, starting with an FIR system. So let us take one FIR system. Okay, so say y of n is equal to summation over say I is equal to 0 to say 2 say ai into x of n minus I. So have you understood that this is an IIR system, FIR system? So if we expand this, it will be y of n is equal to a0 x of n plus a1 x of n minus 1 plus a2 x of n minus 2. So you need, for any present input, for at an instant of time n, if you would like to evaluate y of n, you need x of n at that is the input at that instant, and 2 past inputs. Okay, so it is actually a tapped delay line filter. If we realize it directly, you can see. So here it will be your x of n. Okay, now if I use one z inverse block here, it will be x of n minus 1 here, then one more z inverse block, it will be then x of n minus 2 here. Okay, now x of n minus 2 is being multiplied with a constant quantity a2. Okay, then your x of n minus 1 is being multiplied with a constant quantity your a1, and x of n is, this is your x of n is multiplied with a constant quantity a0. So it gets added here, and finally it's get added here. So this is your yn. Okay, so this is what we call as tabbed delay line filter. Tabbed delay line filter or tabbed delay line systems, also called the transversal system. Transversal system. Okay, why it is called tabbed delay line? Because these are the delay line and being tabbed with the weights A0, A1, A2, A3 like that. Okay, so this is the non-recursive realization. By default it is an FIR system and we have realized it directly, which is a non-recursive realization. So now let us little modify this equation. Okay, so from the above equation, in this above equation, you just replace n by n minus 1. Okay, n by n minus 1. So what you will get? Y of n minus 1 is equal to a0 x of n minus 1, a1 x of n minus 2, a2 x of n minus 3. Okay, then then you subtract that y of n minus 1 from y of n. So what it will be? It will be your y of n minus y of n minus 1. So it will be your a0 x of n, then a1 minus a0 x of n minus 1, right? Then a2 minus a1 x of n minus 1, x of n minus 2, then finally minus a3 minus a2, not a3, minus a2 x of n minus 3. Okay, so you will get these equations. Now let us see this way. So your y of n, you just put this y of n minus 1 that side, so y of n minus 1, then plus, so let us consider different constants. So for a0 is c0, so a0 is equal to c0, so c0 x of n, then a1, these are constant only, so a1 minus a0 is equal to say c1, so c1 x of n minus 1, then plus c2 x of n minus 2, so c2 your a2 minus a1 is c2, and then c3 x of n minus 3, so your minus a2 is your c3. Okay, now look at this. This is the output, the same only, right? Same system only. Thing is that now here you can see one passed output, so it becomes recursive. Okay, so if we now realize it, so it will be your x of n is being multiplied by your c0, then Z inverse block will produce x of n minus 1. Okay, x of n minus 1 is being multiplied by your c1, then again Z inverse will make it x of n minus 2, x of n minus 2 will be multiplied by c2, so these are added. Okay, these are added, then one more Z inverse block, it will be x of n minus 3 and is being multiplied by your c3 are added. Okay, then y of n minus 1 so is being added, so this is your y of n and then Z inverse, and there is no weight, so it is added here. So finally this y of n. So due to this feedback, it becomes recursive realization. Okay, recursive realization. So this is how we can implement a recursive, non-recursive system recursively. But in this case, Tabdil line filter, let me tell you at this point, this is a special case if your this A0, A1, A2, okay, A0, A1, A2, if all the three are equal, suppose A0 is equal to A1 is equal to A2 and is equal to say 1 by 3, then what it will be? Suppose it is A0 is equal to A1 is equal to A2 is equal to say 1 upon 3, so then it will be 1 y of n is 1 by 3 x of n plus x of n minus 1 plus x of n minus 2. So then this is called moving average system. Moving average system. So what is moving average system? This is average because 3 terms are being divided by 3. And moving, this is x of n minus 1, x of n minus 2, x of n minus 3, like that. If it is x of n minus 3, then divided by 4, like that. So it is called moving average system. So in this case, moving average systems, this Tabdil line filter will be x of n minus 1, x of n minus 2. So these weights will not be there, so at the end only there will be multiplied by 1 by 3. Okay. So this is a special case of this Tabdil line filter when all the weights are equal and equal to say 1 upon as many as time. Suppose there are 4 terms, 1 upon 4. If there are 5 terms, 1 upon 5, like that. Then it is called moving average system. So we have seen how an FIR system, which is by default non-recursive, how we can implement it recursively. That is with feedback. Now we'll see an example for the IIR. So let us take another example as IIR example. Okay, IIR example. So suppose now I'll consider from the Z domain, say h of z that is here the transfer function of the system, LTI system, h of z. In case of the IIR, h of z is always some numerator polynomial divided by denominator polynomial. So let us take very simple example, 2 minus a 0.6 z inverse divided by 1 plus 0.5 z inverse. Okay. Now, if we divide this 2 minus 0.6 z inverse divided by 1 plus 0.5 z inverse, you will see a polynomial of infinite length, infinite degree polynomial. Okay, so that means it is not completely divisible. Or 2 minus 0.6 z inverse divided by 1 plus 0.5 z inverse, it is not completely divisible this by this. That's what already I mentioned. In case of the infinite impulse response system, IIR system, impulse response h of n is infinite. So to get the impulse response, infinite impulse response, what you have to do? You have to take the inverse response, inverse the transform of this h sub z. Now if you evaluate the inverse the transform of h sub z, you will get an infinite length sequence, that is IIR. But to make it realize, we can represent it like numerator polynomial by denominator polynomial. Okay. Now directly, if we would like to get the equation, difference equation for this, what we have to do? We have to take the inverse z transform directly in terms of the y and x. So what is y h of z? H of z is your y of z divided by x of z, which is equal to this. Okay, now that is your 2 minus 0.6 z inverse divided by 1 plus 0.5 z inverse. Okay, now if we take the inverse Z transform, what it will be? Y of n, y of z into 1, inverse is y of n, y of z into 0.5 z inverse, inverse is 0.5 y of n minus 1. Similarly, 2 into x of z, that is twice x of n, then minus 0.6 x of n minus 1. So this is your given difference equation. Now you can implement it directly, realize it directly. So first let us draw the input part. So it is your x of n. Okay, x of n is being multiplied by 2. Okay, so let us multiply it by 2. Then here it is suppose z inverse. So it will produce the x of n minus 1. X of n minus 1 is being scaled up by minus 0.6. Then both these two are added. So this is your output. Now this output is get added with, because ultimately I need y of n. So if it is y of n, this will be that side. So it will be minus 0.5 y of n minus 1. So this is your y of n, and that is z inverse your y of n minus 1 here. Okay, then it is being scaled up by minus 0.5 into, so it will be, so finally your this is y of n. Okay, now this is default realization of the given system, which is recursive, because this is the feedback loop, or in the equation you can see this is y of n minus 1, the passed output is present. Now see how we can implement it non-recursive also. So now to realize it non-recursively, say look at this h of z. So h of z is your 2.06 z inverse divided by 1 plus 0.5 z inverse. Now if you divide algebraic division of this 2.06 z inverse by 1 plus 0.5 z inverse, you will get the result something like this. H of z will be your equal to, so you will get this type of polynomial: 2 minus 1.6 z inverse, 0.8 z inverse 2, 0.4 z inverse 3, 0.2 z inverse 4, minus 0.1 z inverse 5, plus 0.05 z inverse 6, minus 0.025 z inverse 7, so on and so forth. So you will get an infinite length polynomial. Now to realize it, somewhere you have to truncate it, right? You cannot simply realize this infinite polynomial. So let us truncate the series that says z is equal z to the power minus 5. Okay, let us truncate it at arbitrarily, just then arbitrarily we truncate it z to the power minus 5. So that means this portion only will take up till this. Okay, so what it will be? Then if we truncate the series or the polynomial at z to the power minus 5, so it will be 2 minus 1.6 z inverse plus 0.8 z inverse 2 plus 0.4 z inverse 3 plus 0.2 z inverse 4 minus 0.1 z inverse 5. Now then if you take the inverse z transform, that means difference equation. So y of n, because it is yz by xz, so y of n will be twice x of n minus 1.6 x of n minus 1 plus 0.8 x of n minus 2, and then 0.4 x of n minus 3 plus 0.2 x of n minus 4 and minus 0.1 x of n minus 5. Okay, then you just realize it like a tabular line filter. So this is also becomes a tabular line filter. So it is x of n into 2, this is your x of n multiplied by 2, then it is x of n minus 1, x of n minus 1 is multiplied by minus 1.6, and then x of n minus 2, x of n minus 2 is multiplied by 0.8, and then x z inverse, it will produce x of n minus 3, x of n minus 3 is multiplied by 0.4, then z inverse x sub n minus 4, x sub n minus 4 is multiplied by 0.2, then z inverse x sub, it will produce x sub n minus 5 is being multiplied by minus 0.1, and then add it up all. So finally this is your 1. So this is how we can realize the recursive system non-recursively. Okay, so hope you understood. So what we have seen in this particular lecture, that what is a FIR system, what is IIR system, recursive, non-recursive, and the recursive system realization of the recursive system non-recursively, and realization of the non-recursive system recursively. Okay, so in my next video I'll go through detail about the detailed realization of the IIR and FIR separately. Okay, for any query and for further question, you please contact me. Thank you for listening.